pero eso es eso.
Hey, thanks guys. That was actually really good on everybody's part. I appreciate that. All right, so let's jump in today. So one quick announcement just to emphasize what was discussed in a moment. So your quiz corrections and retakes, or not, I'm trying to change the word from retake, but I don't know exactly what to call it to remind you. It's not a retake of the same quiz. But if you want to take a new quiz to make up your points from Unit 1, you have till next Friday to do so. Okay? Now, I want everyone to think for a moment very carefully. Okay? Because you don't want to set yourself up at a point that you can't, like a hole you can't get out of. Quizzes are weighted heavily in this class. If the grade you got on the quiz is not the grade you want at the end of the term, you should seriously think about taking the new quiz and getting it where you want it to be. Because otherwise, once that deadline closes, you may not be able to get your grade any higher than a certain point. Okay, because of how quizzes are weighted. So don't be like, oh, it's fine, it will fix itself later. It can only fix itself so much because we only take 3 quizzes, so there's not very many points that go into that category. The way it divides up is almost every point on the quiz is equivalent to a percentage of that category. Okay, so keep that in mind. Zayd and then Raquel.
So I didn't turn in my packet for the pink sheet. Am I just kind of screwed on that?
So with homework, we don't ever turn the packets in
Well, no,
fully.
I'm saying like I didn't submit the homework assignment on Canvas and now it's locked.
If they have stamps on them, you didn't need to.
Okay.
If it doesn't get a stamp and it doesn't get put in, you can turn it in after the unit closes, but it's only worth 60%.
But 60 is better than
But
0.
it is better than 0. So if you have it done, then you can turn it in.
That's good math.
Okay? So, Raquel, question. Next Friday. So, and a reminder too that because I know I'm only here on A days, so you can always take with me on A days, but if you ever want to take it on a B day, you can do what Tessa did, and she signed up for the testing center and took it there on a B day. Okay? So keep that in mind, you have that as an option too. Okay? Any questions on fixing quiz grades? Maybe how we should say it? All right. Today by... All right, today we have 2 new key vocabulary words that we're going to be focusing on and understanding them. If you look at our I can for today, our I can is differentiate between this thing called fission and fusion and from nuclear decay. So we already have learned about nuclear decay. Can someone by raise a hand remind us what is nuclear decay? What is that process of nuclear decay? Can anyone remind us? Good, so gamma falls under nuclear decay. Have a smiley face, Sasha. Someone else add to that? Kenzie? Alpha is a type of decay. Have a smiley face, Raquel. Beta, have a smiley face. Megan? You got it. Positron emission. Okay. Boston? She said positron emission. But can someone give us, so we're saying words, which is good. All right, I'm talking, you shouldn't be, unless I pointed to you. Can someone give us like a sentence though, or a visual, like what is radioactive decay? Jane?
It's when like the neutron to proton ratio is off balance, so it has to kick one out.
Perfect. So all these things they mentioned, which are part of it, happen because the nucleus is unstable, proton to neutron is off, and so then it kicks them out to turn into something that can become stable. Now, nuclear decay is a process, happens all the time, happens on its own time. That time is the half-life, right? Sometimes fast, sometimes slow, okay, but it just happens. Fission and fusion, which we're going to learn about today, are other types of nuclear reactions, and in some cases they do happen on their own. But I want to make sure, we want to be able to differentiate and understand the difference, okay? So fusion involves joining 2 smaller nuclei. Everyone take your hands with me, ready? Go like this. Make a visual. Fusion is fusing together 2 smaller things to make a bigger one, right? We had a question on our Unit 1 quiz that was about fusion. It talked about someone making a new element, right? We watched a video with Iron Man doing it, of the idea of if I form two things together, since this new thing here since this new substance here has more protons together, it's a new element, okay? Now, in the process of fusion, once again, chemistry a lot of times, like in picture form or symbol form, can look very simple, because it's just like, oh, 2 + 1 = 3. In actuality, getting fusion to happen is a lot more difficult. Yes, Caleb?
So how many, can you ask, is there ever a limit, like how much, like, elements you can add together to confuse?
So that's the difficult part, is it's one thing to like put them together, but then to actually stay together can be very tricky. Because of that idea of you need that perfect proton to neutron ratio, otherwise it just falls back apart. So we'll kind of look at a chart at the end that will kind of answer that question for you. Have a smiley face for that. So in order for fusion to happen, you need a minimum temperature of 72 million degrees Fahrenheit, which is the sun. So this does happen naturally, but as of right now, have a smiley face, right? Only in the sun. Now this is another thing actually another superhero movie addresses. If you've seen Spider-Man 2 of the originals with Doc Ock, I don't remember what he's trying to accomplish.
He's trying to like fuse something, fusion stars.
Yeah, he's trying to make fusion happen on Earth, right? He builds like a sun, right, in that little chamber. That, in a sense, scientists are trying to still do that. They often call it cold fusion, because they're trying to find a way to make fusion happen without needing this high of heat, okay? So fusion, the process of two smaller things coming together to make something bigger, okay? Now, as we mentioned, this is the process that happens in the sun and stars, because our sun is a star, right? Okay? So this process happens, and the heat and light that we see from the stars is part of that energy. So a big thing we're going to look at here with our differentiation is understanding the energy difference of these three things. Okay? Because of this process, this is actually where all elements are created. We'll watch a 3-minute video here that kind of shows you it in a visual way. Okay? Does everyone have those blinks like in our video? Okay, as we watch this video, what I want you to notice at the end, you'll get a smiley face if you can tell me, is what is the last element made in the star, okay? So watch the video and then see if you can identify that. Don't say it out loud when you hear it, just make a mental note. Oh, let me plug in this. Not loud enough.
All the atoms in the universe heavier than hydrogen and helium, forged by stars.
Stars are really interesting. They don't just sit there. They know because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. A star begins its life made out of hydrogen and helium mostly. About 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spend.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel this stellar furnace. And so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing blowing up. You made a supernova.
The supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
zirconium,
terbium,
thorium, iodine, xenon, cesium, barium, lanthanum,
tellurium,
cerium,
actinium,
actinium,
xenon,
thorium,
protactinium,
protactinium, uranium. Done. That's enough elements.
Okay, don't say it out loud yet. On a count of 3, you're gonna shout out the element that was the last one made within the star. Ready? 1, 2, 3. Prematurely because I'm scared. False start. It is that iron. Have a smiley face because you are correct. So we'll look at a chart at the end that deals a little bit more with this. But the basic idea is that every element was made at some point from a star. Right? So there's a cool poem, and then the newest Disney movie has a song. I can't remember what the song's called. Oh, the movie Wish, if you've seen that new cartoon. Right? You probably don't unless you have small children at your house. But my daughter loves it. Right? But in it, they sing a song about how we're all stars, which in a sense we actually are, because all the elements inside of us are created from stars originally. Okay? All right, now we're going to do the opposite. Ready? We're going to take your hands, clasp them together, clasp your hands together. Okay? So fusion was coming together, fission is breaking apart. Not so. Actually, the supernova is still fusion. So fusion has a lot of energy too, and we'll do a comparison here in a second. So in fission process takes a large nuclei, and it splits into 2 smaller ones. Now, this process does not happen spontaneously, meaning it doesn't just happen on its own, right? If you have an unstable one like Jane brought up, if the proton to neutron ratio is off and it's unstable, it won't just do fission. It'll do alpha, beta, positron. It'll do one of those to become stable. But if you throw one more neutron into this already unstable nucleus, that's when fission happens. So you kind of have to like tip it over the edge of like, I'm unstable, now you've given me one more. That's what causes fission to happen. Okay? And this is what happens in a nuclear bomb. So a nuclear bomb is the process. Give me attention here, everybody. So a nuclear bomb is the process of taking an unstable nucleus, typically they use uranium or plutonium, they shoot a neutron into it, and it causes it to split. In the splitting process, all that nuclear binding energy we talked about that holds it together gets released. Now, it's not just one atom, it is a chain reaction. So let's watch this video that gives you a good visual in your head of what we mean by a chain reaction.
Alright, teachers love mousetraps because they're a great lesson in potential and kinetic energy. So potential is energy that could happen.
Yeah.
And then kinetic energy is moving energy.
Okay.
So if we set this mousetrap,
Yeah.
and there we go. And I'm going to put a ping pong ball on it. Carefully.
Because
And
mice love ping pong balls?
Well, it's a good demonstration. So when this flips, it'll take all that energy it's storing and release it.
Yeah.
So I'm going to drop this on there, and then we're going to see if we can get that ping pong ball to fly.
Okay.
Alright, so here we go. Ready, and... That's a good 30 feet.
Okay. That was a crappy trick, by the way. I mean, that's nothing like the foam already. We should have started with that, probably.
Well, we got the idea. That's a lot of energy in one mousetrap.
Yeah.
But what if we picked it up just a little bit and tried it with a couple...
10 million mousetraps?
Well, we'll start with...
That's beautiful.
There it is. You have amazing prop department.
Okay, I want to pause for a second. So the idea here is, right, is an unstable nucleus has a lot of potential energy within inside of it. Okay? And then they're going to drop one ping pong ball, which represents just sending one neutron into it. Okay? Oh, stop that. I want to hit play.
Space bar.
Right here.
Alright, teachers love mousetraps. Potential and kinetic.
That's beautiful.
There it is. You have amazing prop department here.
Yeah. Boy, they must hate you right now.
Alright, so
Incredible.
what we're going to do is we're going to trip this by just throwing some ping pong balls in. We'll see
Okay.
how many it takes to actually start it, and then we'll see if it can release energy.
Should we throw them all at once or throw them individually?
Let's start with one and go from there.
Okay, all
So
right.
it's also actually a model for Newton's third law. It's a model for how fission works. It's a really...
Okay, nothing happened.
You got a lot.
Oh, you got a lot. Okay, all right.
Go ahead.
Middle up. Oh.
Alright, teachers love mousetraps because they're a great lesson in potential and kinetic energy. So potential is energy that could...
Okay, so the idea once again in fission is one, right, does have a lot of energy. But in a nuclear bomb, it's not a single atom inside of there. It is obviously zillions of them, and we get this chain reaction where as soon as one splits, in the process of splitting, it sends out more neutrons. Those neutrons, like the ping pong balls, then can hit other atoms, causing them to split, sending more neutrons, and you get this giant chain reaction, meaning immense amount of energy. Okay, so to help us compare the differences of energy, we're going to use an interesting simulation, but I used it every year, and it really helps nail the point down. Okay, let me open this up here real quick. Okay, so in this simulation, you can drop different types of bombs in an area and see the blast radius.
Okay.
Okay?
Wow.
Yo a lo mejor no hubiera tenido amigos sin apuro. Porque bueno, mi amigo que me cruzó todo el grupo era japonés y él era de Kioto. Increíble, hermano. Increíble. Ese pequeño detalle, hermano. Ese pequeño detalle.
Okay, now,
For real, Leo. No, for real, Lehigh.
I want to see my diamonds.
Dude, all the elements.
okay, so the reason why I picked Sky Ridge is so that you understand the blast radius, because you know this area. Okay? If I just do some random place, it's harder to understand like how big that is. But you guys can kind of, from here, you can be like, oh, my house is over there, right? So that's why we're dropping it on sky ridges for the purpose of understanding the size of the blast. Not because I don't like sky ridge at all. Okay? All right. Now, once again, the idea is to compare decay, fission, and fusion. Okay? Now, decay has no type of massive energy that comes out, right? It's happening in this room as we saw with our Geiger counter, right? So that, in terms of high energy, is very, very low, okay? First one we're going to do is a simulation so you can see the difference between nuclear and chemical. So a nuclear reaction deals with the nucleus. A chemical reaction deals with the electrons. So a chemical explosion is like TNT or missiles, those type of things. Those all work through a chemical type of reaction. Okay, so that's the first one I'm going to show you. It's not actually because this one only does nukes, but just to give you a comparison of, it would be about the same amount. Okay? All right, so let me...
We'll do the fat man one. Do the fat man one.
We will.
Sorry, what?
No, do the little boy.
Igual que acá entrego un día antes.
Fat man.
Okay, so this one is to simulate a large chemical explosion. Okay?
Oh. Hey, I'm not dead.
Now, if it was just chemical, everybody.
Eagle Crush is dead.
So here's what the different colors mean. But if it's just a chemical explosion, it wouldn't have any of these other, like it's not going to have radiation or things like that. It would really just be this red inner circle. So in terms of like missile, TNT type explosion, like they can be very dangerous, right? And they have a lot of energy within them. Okay? But let's now compare it to, the first one we're going to do is a fission bomb. So what, show me with your hands what happens in fission?
Boom.
Good, so 2, 1 becoming 2.
Fat man.
Okay?
No, do the little boy.
Alright, so
Yeah.
Let's go.
this one is this is actually the bomb that they dropped on Hiroshima. This is the name of it and how they did it. Or sorry, this was Nagasaki. Little boy was Hiroshima.
I was gonna say Hiroshima, I was like,
Bueno, una de las dos. Entiendo.
The other one, so this one right here. So little boy was Hiroshima and then Batman was Nagasaki. So, okay, ready?
oh,
Okay, I'd be dead.
I'm still alive.
So this is heavy blast zone. This is radiation. Orange is thermal radiation, which means if you're in that, you're still getting up to 3rd degree burns. Okay?
I'm in
If you're inside the orange.
if I was at my dad's house, I'd
Okay? So if you can't quite see, so we are almost to Low Peak High School in terms of the biggest. And this is like Thanksgiving Point Gardens.
Oh wait, no, I'm safe. I'm safe. I'm safe.
I'm dead.
So in terms of energy, right, that's a lot of energy that comes out in that process. Okay?
Put on Long Beach.
Okay, I probably get the last one.
It's a little boy.
Okay. What type of energy was that? Was that fission or fusion?
Fission.
Fission. So now let's do a fusion and compare.
Little boy.
Wait, how can you have a fission or the one where it goes like this?
Yeah, so in a fusion bomb is they force 2 typically hydrogens to come together.
Oh, and then they make chemicals and then
Yep. Yep. Okay, everybody ready?
Oh, I'm dead. This is a fission, right?
Yeah, this is fusion. Last one was fission. This is fusion.
This is gonna be big. Yeah.
All day, I should be living.
I'm dead.
I'm still alive.
we should drop.
Oh,
I don't want
Now, notice a few differences. So number 1, what has more energy, fission or fusion? Fusion, right? Fusion has so much more energy than fission does. what do you notice? There's a ring that's not in this process.
No green.
Good, Bodie. There's no radiation when it comes to fusion. Okay, you have a smiley face, Bodie. Okay, that's one of the things. So this is obviously a negative side of using fission and fusion. A positive side, and we'll have a whole unit about energy, is harnessing this energy to power our lives. And that's why if we could find a way to stabilize fusion, right, we could literally power the entire world with very small amount of resources and no waste whatsoever, right? There's no smoke, no carbon dioxide, no pollution that comes in the process. Okay? Yes?
But that doesn't really explain, like, how do they time it to go off?
Yeah, how do they time
When
it?
it hits the ground.
That was my question, is how do they time it?
So if we have time at the end, I'll show you. So this bomb that we just showed, so there's only been 2 times in human history that we've used nuclear weapons. And that was us in World War II, right? Outside of that, it's never been used on humans. These ones, though, have been tested. So these do exist. They're not theoretical, and they are tested. There's a video of when they tested this bomb. It was made by Russia. And it's interesting because they have to put parachutes on it to slow its fall so the airplane has time to get away. Because the jet can't get away fast enough for it to, when it explodes. Say that again? Not really, because it's not so much of the impact that causes the damage, it's the reaction itself. The mushroom cloud that came from this test was taller than Mount Everest.
That's insane.
Yeah, can you imagine? So Russia has a lot of empty, barren wasteland, like Russia's really big. What's really sad is when we first started nuclear testing, though, and we didn't know about the dangers of it, they actually tested in areas, not on people, but they used to test in Nevada a lot. Yeah, and so there was a lot of people years later who, it was called fallout in this one community where they all got cancer because it was too close to the testing. But they didn't realize at the time that harmful side effect. So it's the radiation. Yeah. Yeah, still tons of heat and energy, but it doesn't have. The thing with fission is it breaks up, but the things it breaks into are typically still radioactive. Because radiation can cause it damage. So, okay, show me one more time, everybody. Oh, actually, we'll look at this. And then we'll do our review.
Is there anything bigger than that?
That's the biggest one. Sorry, Bumba. As of right now. Okay, so last thing to wrap up here, and then we'll work on our assignment, okay, is so this idea of everything came from fusion in the stars matches the distribution of elements in the universe. I'm not going to go on, I'm just going to pull up a little graph here. So in the entire universe, this pie chart shows the distribution. This blue section, which is almost 75% of all elements in the universe, is hydrogen. Because, all right, listen here. Yeah, hydrogen is the initial Lego piece. All the other Legos have to be made from it. And then it gets, helium is the next big section because it's the second thing that gets made. And then after that, it just goes down. Okay? Now going back to, the thing Caitlin brought up, this idea of knowing, are things going to do fission or do things more likely do fusion, there's kind of a tipping point, and we saw this graph before. Okay? So fission occurs if the nucleus can decrease its energy best by splitting. Fusion happens if it's better that it combines. Okay? So obviously fission happens with things that are already really big. Because if it's already big, it's more likely to break apart. If they're small, then they're more likely to go through fusion. Now it's not split right in the middle of our elements. We see once again, we should have this graph here, that iron is the break point. So add these, are these arrows drawn on your chart?
Yeah.
Fission and fusion, okay, perfect.
Yeah.
So everything to the left of iron is most likely to go through fusion. Everything to the right is more likely to go through fission. Questions on that?
No aprendimos nada hasta la secundaria.
Okay, don't say this out loud. Zip your lips.
Which one was Big Bomb, Fission, or Fusion?
Fusion comes together.
Fusion.
Oh, Fusion.
So this has more energy than this.
This is fusion, right? And this is fission.
Yeah.
Okay.
Think of, because coming together is like the sun, power of the sun explosion.
Oh, yeah.
Right? Okay, don't say it out loud. I have a question for a smiley face, but don't say it out loud so you don't ruin it. Okay? Based on what we just talked about, will lithium more likely undergo fission or fusion? Don't say it out loud. Figure it out, and then it's not on your paper, but there's some empty space. You could write your answer at the bottom there.
Will lithium be more likely to fission?
Good. Write it down. Don't say it. Just write it down. Write it on your paper.
Funciona, weón.
It's pretty much the question is can you read the graph?
No, but like it says it up there.
Yeah, if you read the graph. Okay, show me your answer by showing me the sign. Is it fusion or fission? I said that backwards, but I didn't know.
She did the right hands.
You said fusion. Have a smiley face here.
Is that like
Hydrogen bombs?
hydrogen, but then once
Sí, les manifest.
So yeah, so like the fusion bomb, another name for them is a hydrogen. No. Do you feel like you've heard of that before? No, I don't know. Maybe. I don't follow up a ton on the bomb making going on in the world, but I wouldn't say it's not out of realm possibility because you could do fusion with helium. So, okay, let me know if it's a real. Okay, on your assignment, I need 30 more seconds, and then I'll stop talking. You get to work. Eyes up here, everybody. Eyes up here. On our assignment today, we are going to be looking at that kind of what that video showed of how everything starts with hydrogen and it eventually turns into iron. So this assignment is similar to decay, except this time we're not using alpha beta positrons. We're seeing what elements they're turning into. Okay? Now, the key at the top can kind of be a way to check yourself. Meaning after you put in an answer on a blank, you should see if it matches something up there. If it doesn't, then you've done something wrong. Okay, and then if it does, you can kind of cross it off, I've used it. Key point with all equations is arrow is the equal sign, and it must be balanced on both sides. Okay, once you finish this, there's some follow-up questions on the bottom and on the back. As always, if you get done before time is called and you want me to pass it off and stamp it for you, you can. Otherwise, you'll need to finish it up on your own. Okay?
Can you stamp our ones from last time today, or do you want?
I'm going to wait till the last 3 minutes because I want you to focus on this assignment right now. But in the last 3 minutes, if you want me to stamp off your penny lab, I can.
Okay.
Okay? All right, get to work. Let me know if you have any questions. If you can wait until the principal has come back to the office, that would be great.
Okay.
Great.